Good evening, everyone. Welcome to this session of Astro Adda, a series of popular astronomy talks organized by Nehru Planetarium, Nehru Memorial Museum and Library, and Public Outreach and Education Committee, Astronomical Society of India. And we are moving towards gravitational waves, I think, for the first time. And we are really so fortunate to have with us Professor Tarun Souradeep, who is leading one of the leading figures in India's steps towards gravitational wave endeavors, and also part of the very first paper wherein gravitational waves were detected in a way, I mean, revolutionizing the way we are looking at the kind of multi-messenger kind of astronomy possibilities that we are having. And Professor Tarun Souradeep from IISER Pune, and also from Ayuka. And I think also you were there at TIFR and several places, and he has many awards to his credit, including breakthrough for the very first, the gravitational wave detection paper. Tarun, I will hand over to you,
Okay.
and when you ask me, I will put your screen share on, and this is to all the speaker, all the participant viewers, that Tarun would not be able to see your questions if you put out your question. I already see many comments. Perhaps there are some questions coming in, and so just be aware that questions will be answered towards the end. I'll hand over to you, Tarun.
Okay. Thank you very much, Ratnashri, for the invitation. It's a pleasure to be talking to young people about some exciting science goals that one can have in gravitation and cosmology. So today I chose to talk about a slightly more futuristic quest that I hope we will be on in a decade from now, and that is the quest for cosmic origin. Okay, and that involves, interestingly, two areas of astronomy and astrophysics that I am very familiar with, both and gravitation cosmology. So it has gravitational waves and the cosmic microbackground, which is one of the most important observables that we have to understand our universe. Okay, so let me begin my talk. So I'll be talking about the quest for cosmic origin. And before I go there, let me show you that the cosmos is very pretty. And here's a picture courtesy Dorje Anchuk, who is an astronomer at the Leh Observatory, Indian Astronomical Observatory in Leh, of the entire Milky Way. But the Milky Way is just our own galaxy. If you know, it's just our home in the cosmological sense. Before going to this quest, let me spend a little minute, since I am the spokesperson of LIGO India, to mention that underway now is an interesting and exciting quest that India is already part of, which is LIGO India. We are building one of the gravitational wave observatories on Indian soil in little town called Aunda in Hingoli district of Maharashtra. The closest big city you may be aware of is Nanded, uh, which is about 60 kilometers away. And we have acquired the site, and we are in the construction phase. And one of the buildings is already, sort of coming up. And so let me now, last few years, I have been sort of focusing my thoughts more on the next big quest we could be getting into, and that is the quest I'll be talking about. And this is a quest in cosmology, and it is also the quest to understand the origin of the universe. Okay, so it's a very prized quest, and interestingly, it involves gravitational waves, but we'll get to that then. Let me tell you a bit about the universe while we get to that, before we get to that. So at this point, there is one window which is open to the gravitational waves in gravitational waves to the universe. So we can see the universe in gravitational waves observed by these LIGO detectors, which started in 2016. By now, we have many sources of detected many instances of mergers of black holes and neutron stars, and very exciting science and astronomy is coming out of it. But of course, and LIGO India will add a huge thing to it by allowing astronomy with it, gravitational wave astronomy. So that's one window, but there are other windows. One is a space based gravitational wave detector called LISA, which is expected to come up somewhere in the mid 30s, 2030s, which will detect sources of a similar kind. I should mention the LIGO detects sources of time periods of milliseconds, and these are also relatively close by in cosmological sense. But LISA will detect black hole mergers, which are the big, massive, supermassive black holes at the center of galaxies, and those sources will revolutionize our understanding. And black hole mergers as well as black holes falling into such massive black holes and other sources. Then there's pulsar timing array, which can open up anytime now. In fact, last week at the uh, American Astronomical Society meeting, there were tantalizing hints that there may be already signal present in the current data of the pulsar timing array. But I will be focusing on this window, and this there's a question mark as to when it will open. But actually, technically, we are very close in technologically. Uh, uh, we are very close to measuring gravitational waves which originated at the beginning of the universe. Okay, and this is in the cosmic microwave background, and in fact, in the linear polarization pattern of the microwave background. And these gravitational waves, when detected, will be unique from the other three because these have a quantum origin. They originate in quantum theory applied to curved universe, curved space-time, and so these would be exciting step towards understanding quantization of gravity, and it's going to be a fundamental breakthrough. So let's go back and talk about the universe itself. So the universe, as I told you in the first picture, is very beautiful. But what we really appreciate from Earth, looking out with naked eye, is essentially the Milky Way. Largely, you will go to a very nice dark place with clear skies, and this is a beautiful picture reflected in the lake. And you can see there's lots of stars, but these are all of from our own galaxy. If you move off the galactic plane to somewhere here and choose some dark spot where you don't see any of our foreground stars and zoom in with the most powerful telescopes we have, and everyone must have heard of the Hubble Space Telescope. And this is what is called an ultra deep field image of a small part of the sky, tiny part of the sky. And you can see that there are literally thousands upon thousands of galaxies and stretching far away, so far that light traveling from those galaxies originated when the galaxies were themselves forming. So some of the splotches that you see, which don't look like typical galaxies, are actually galaxies, but they are not formed yet properly. They are kind of just forming. And every little splotch here is actually a galaxy. So the universe is full of galaxies, and we really need to understand the structure of the universe, how what is there in the universe, and if also we would like to understand where did it all begin, right? And how did it all begin? And that's the quest, and one of the most you know kind of prized quests of mankind is to understand our own origin, the origin of the universe we are inherited. So to do cosmology, we actually treat a galaxy like our own Milky Way, just like a point particle. But before I do that, I wanted to point out that the galaxy itself is huge, right? It stretches so big that it takes 100,000 years for light to travel from one end of the galaxy to the other. Okay, so that is the kind of scale on which these stars, about 100 billion stars, are held together by gravity around in beautiful spiral structures, or kind of more messy elliptical galaxies. And each star there, even if you take the sun as a reference, is about 10 to the 30 kilograms. So it's a massive uh, object that we are talking about when we talk about a galaxy. But on the cosmological scales, these are just like dust particles tracing the fluid or the air in a room. So often we study the airflow by looking at the dust particles moving around, and we don't care about how the dust particles themselves look. I mean, there are people who care about it, and there are people similarly who care about how a galaxy forms and how a galaxy is held together, and their entire careers and generations work on that. But for the kind of cosmology I'm talking about, we will be just peering into the universe and looking at the distribution of matter in terms of how many galaxies are there at various places. So this is kind of an atlas, local atlas of the distribution of galaxies in our neighborhood. So we are at the center of this spherical distribution that is shown here. And the cloudy structure that you see here are actually clusters of galaxies. So each spot there is a galaxy itself, and these spots are so densely together that they look like clouds here. And this is our local neighborhood. This is our neighboring big cluster called Virgo cluster. And then there's a Comac supercluster. And this is our local map. If you're doing Star Trek and heading out of our galaxy, then this is the kind of roadmap you will have. But this again, on cosmological scales, although it's a huge volume of space, you can see that there's a stick here which shows you 100 million light years. And that's this tiny stick at the top. I'm not sure if you can see my pointer though. And then this kind of tells you the scale on which we are talking about when we talk
Pointer
about
is
a
visible.
pointer is
Sorry,
visible.
pointer is visible. Yes, it is visible.
Okay, thank you. So you can see that this little pointer tells you it's 100 million light years. So this whole volume is huge, right? So it takes millions and millions, hundreds of millions of years to go across this volume. But this, again, in the cosmological scale sense, is our neighborhood, right? So if we take a map of the all the galaxies that we can see and plot it out, it would look something like this. And this is again not all the galaxies. This is not the entire atlas of galaxies, but this is typically how a region of the universe looks, with lots of galaxies here. And essentially, as we move in the video, you can see that you're flying through this distribution, and kind of seeing clusters of galaxies passing you by. And then there are sort of, we are trying to home into something like our own galaxy, and you can see that we are part of some kind of a galactic network of galaxies everywhere. And the question is, where did this interesting rich structure in the distribution? You can see that galaxies are not uniformly distributed at all. They are forming a network, very interesting network of filaments and voids, which sort of is very visible and apparent in this animation. And Let me let you all appreciate this. So you can see we are slowly zooming into one part of the universe, but as you see, the network goes on and on. So the question is, so how do we understand such a universe where there are lots of galaxies? Each galaxy is huge, massive, but kind of they're distributed in a very interesting pattern. And for that, we actually invoke some symmetries, in the sense we try to see if there's some simplicity in the distribution. And indeed, we started by assuming that the distribution of matter around us is the same in every direction. And this is kind of borne out by this picture coming from the 1970s, which is the picture of the galaxies. It's a plot of the galaxies only on the sky, it doesn't show the distance away. And you can see no part of the sky has enormously larger number of galaxies than the other. There is, of course, some kind of graininess and coarseness, but if you look at it with coarse eyes, and if you have bad eyesight, you can take care of your glasses and you'll see more or less uniform glow on the two hemispheres. And mathematically, if we assume that we are not at some special point in the universe, such that the universe is isotropic around us, or the universe is this mass distribution is the identical around us, and we sort of assert that it will be this isotropic, or it will the same property will hold around any observer in the universe anywhere, then it naturally leads to a very simple model where it says that the distribution of matter is homogeneous in the universe, right? And that, although it's a simplifying thing, actually leads to one of the biggest surprises in physics, because that tells you that the universe has to be expanding, or mathematically it could be contracting too, but we know it's expanding from observations. So, but it cannot be a static universes are very rare. I mean, it's not, these are not stable solutions. So essentially you have a situation where you're forced to accept that space time itself expands, and space expands in time, right? If you look at the universe evolving in time, then this universe, the space in the universe, the three-dimensional space, is expanding in volume as with time. And this is nicely depicted here in this animation. And this is, of course, it shows a regular lattice of points, not really the distribution of galaxies. But the idea is that there's a space-time fabric which is, expanding with time, right? And it's taking the galaxies apart with it. It's not as if the galaxies are moving in any sense. Okay. And this expansion has very, very interesting consequences itself, which are very counterintuitive. For example, you can see here two galaxies from where there's a simultaneous burst of light. You can see the red arrows which show you the light moving, shell of light moving, is slowly feeling kind of tired as it moves out. Okay. And that is because the space-time is expanding, and although light travels at the same speed, there is more volume to more distance to cover when it wants to get from one galaxy to the next. Initially it covered one galaxy to the other in some time, but by the time it got to the third galaxy, it finds it that the space has expanded. And these are very interesting consequences, and this is the basic consequence of doing cosmology. It's like doing basic physics, but on a membrane that is stretching, or on a space which is expanding in time. And that is our view of our universe. So if you want to ask how much do we know about our universe, or what do we know, so we believe if these models are correct, then our universe is expanding from some point in the past along some trajectories. The size of the universe increases by some kind of pattern. So it could be increasing and then contracting back, or it could increase and keep increasing at the same speed, or it could kind of, taper out at the end, or it could expand at ever faster speed. And that we know from our model depends on how much of the matter in the universe clusters under gravitation and how much of the matter does not cluster under gravitation. Now, we are aware that gravity is an attractive force. So typically one expects that there will be always matter. If you have a uniform distribution of matter, it will try to cluster together. But if what also the Einstein's theory of gravitation told us is that pressure also gravitates, and if we have exotic kind of matter, and particularly something called vacuum energy, then the pressure comes out to be negative, and it cancels this attraction of matter. It actually counteracts that, and in fact, there's a ever expanding universe that is expanding faster and faster with time, which is shown in the red curve. Okay, so essentially, to understand our universe, we needed to understand three things: how much of the matter clusters under gravity, how much of the matter does not cluster under gravity, which I'll call vacuum energy for simplicity, and what is the curvature of the universe, because the universe is a smooth it's distribution of matter, which means it's a smooth space evolving in time. Of course, the space is expanding, but it's the same everywhere. It's a homogeneous, like a piece of paper, but a piece of paper is geometrically flat. But it could be the surface of a ball, then it's geometrically curved and geometrically positive curvature space, which is expanding in time. Similarly, you can have spaces of negative curvature, and that is the third unknown that we were faced with. And these were totally unknown at the time, even in 1990, when I started my research. Okay, but at that time we knew that cosmos has to be understood in terms of its expanding universe, and that itself has interesting consequences. One is the fact that light coming from a distant galaxy looks redder, in the sense it's redshifted, or it is seen to be at larger wavelengths or smaller frequencies. Okay, and this is can be interpreted as if the object is moving, just like a Doppler effect of some source which is moving away from you, is to reduce the frequency. You can imagine it to be that, but the right picture in cosmology is that space is expanding in time, hence the galaxies are moving apart, and that is what causes this redshift, which is kind of encoded in the Hubble law. The farther a galaxy, faster it seems to be receding from us, or more is the redshift. Okay, so redshift is a measure of distance in our galaxy, and also a measure of how far back in the expansion is the light coming from. If we see the same hydrogen line but at a different frequency, then we know that it originated from a galaxy at a particular redshift, right? So in particular, if it is at a wavelength twice of what is the normal wavelength, then you think you would infer that the galaxy is at a redshift z of 1. Never mind all that, but the expanding universe itself has very, very interesting consequences. And I was telling you about the expanding universe to actually bring home one point. So if don't get all the details, remember one point, that a part of the universe, if I'm monitoring a box in the universe which has the number of galaxies here, that box increases in volume in time. Okay, that's an expanding universe. So it's the same galaxies, but they are kind of moved apart from each other because the box itself has become bigger. Okay, so here is the box. At some stage, here it is become twice as big and again twice as big, right? And then if I want to ask the question, how does then the density of galaxies evolve in time? You can see that it's easy to see that it will be 1 over the box size, right? And if the box size is half, the number of galaxies will be 8 times larger, 2 to the power of cube. And then if it is 1/4 the size, it will be 8 times larger. Okay. But radiation has an additional thing. I told you radiation from the past also changes in frequency. As the universe expands, the frequency becomes lower and lower. And the energy of a photon or light is given by its frequency. So, for radiation in the universe, as the universe expands, the density falls off faster, which means going back in time, okay, the density of the radiation grows faster back in time than the density of matter. So at this point, we know that the density of radiation is about 1 part in 10,000 of the matter density. But if we believe that the universe expanded from very small sizes to now, then there must have been a time when the universe was 10,000 times smaller than what it is now. And the density of radiation was equal to the density of matter. And for any time before that, the universe was entirely dominated by radiation. Okay. And so the early universe would have been totally radiation dominated. And that makes for life very simple. I mean, you don't have to worry about if I'm talking about the universe and where it originated. I have to think of a universe full of radiation, a hot universe full of radiation. Okay. But where is that radiation now? Okay. And luckily, we have detected that radiation. And we detected it way back in 1965, rather serendipitously, when one of the early radio telescopes set up by Bell Labs was trying to measure things very accurately and couldn't get rid of a noise which seemed to come from every place in the direction in the sky at all times. And this turned out to be the cosmic microwave background. This is the glow of that early radiation dominated universe. And this is the dominant radiation content of the universe. And it dominates all other radiation content, although we have more energetic sources like X-ray, gamma ray sources. But in terms of sheer amount that these contribute to the energy in the universe, the cosmic microwave background accounts for 99% of the energy density of the universe. It's also extremely isotropic, which means that our assumption that the universe is the same in every direction that we look at, okay, remarkably same, is quite well borne out. In fact, the microwave background looks the same to 10 parts per million, right? So the temperature of the microwave background, which is now measured to be extremely accurately to the third decimal point, is a Planck distribution. It's a black body. It's really like a glowing hot body, okay? And it is at a temperature of 3 Kelvin now. But remember that when the universe is 10 times smaller than it was now, that the temperature would have been actually 10 times higher. When the universe was 100 times smaller, it would have been 100 times larger. Okay, so going back, as we go to the early universe, when the universe was 10,000 times smaller, as I said, when radiation became as energetic as the matter distribution in the universe, at that time the universe was 10,000 Kelvin, right? At that time, it doesn't matter whether you're talking in Kelvin or Celsius, right? But it's about it's as hot as it's hotter than the surface of the sun. Okay, now let's try to see where are we seeing this as the cosmic microwave background. So not only is this giving you all the radiation in the universe. It's a sample that we measure when we measure cosmic microwave background. We are sampling the pristine radiation, which originated from a plasma screen when the universe was only 500,000 years old. The universe now is about 14 billion years old. So we are really looking at a baby universe. Okay. So if we look at a 100-year-old person, this is a 1 day old baby. Okay. So this is how far we can look back before the universe actually does not allow light to penetrate through, because the universe is a hot plasma before that. Okay, so this is a plasma screen surrounding every observer in the universe, and we are lucky that we are able to see this glow through our own galaxy and all the emissions very clearly, all the way 43 billion light years away. So this is IMAX theater. I'd like to call it, like we are actually sitting in a IMAX theater where we can look all around us, and we are seeing this glowing plasma screen, which is 43 billion light years away, right? And it is actually at a temperature then of 3300 Kelvin. But because of the expansion of the universe, by the time we see this radiation come to us, it is at a 3 Kelvin temperature that we see now. Okay, so this is setting the stage for where we are seeing our signal from, the cosmic microwave background. Also, you should remember that you can think of this screen as a physical object. It's like a shell which is surrounding us, a shell which is 43 billion light years in radius around us. Okay, and anything that happens on the shell is going to show up in the distribution of the light coming from this plasma screen. And for many years, this plasma screen looked very dull. It was the same temperature everywhere to the extent that you could measure. Till we got to early 90s, when we started our research, when I started my research, with the Cosmic Background Explorer, seeing the first glimpses of fluctuations on it. And that was heralded as a signature of the fluctuations that gave rise to this rich distribution of galaxy structure in our galaxy distribution. Remember, we flew through this galaxy distribution. This is the atlas I was talking about. So if I map out all the galaxies that we see here, you can see there is like a spongy kind of distribution around us of galaxies. Okay. And a typical volume of the universe, the galaxies are organized in this rich structure. And this fact that this distribution of galaxies is not, dull and uniform, actually is reflected in these tiny fluctuations that you see in the microwave background temperature at the level of 10 parts per million. So 10 to the minus 5, right? So this is the 3 Kelvin glow that we see, and on that there are about tens of microkelvin fluctuations that you can measure in different directions in the sky, and we've been able to do that with increasing accuracy over the decades starting from 1990. Okay, and that sort of tells us how the galaxy form these intricate structures that we see now. Where did these superclusters, clusters, and these big voids in the distribution of galaxies arise? They arose from these tiny inhomogeneities on the plasma screen when the universe was only 500,000 years old. Okay, and now it is 14 billion years old. So these are really tiny perturbations in the early universe. Now that is the first part of cosmology, and we have almost mapped it all out. All the information that you can get from this fluctuation here to this large scale structure here. We understand our universe very well, and I'll tell you how well very soon. But the question we'll be asking is, where did the fluctuations that we are seeing in the microwave background arise at all? Where did they come from? And we believe that they came from a very early phase in the universe where the operating physics is at such high energies that we will never access such energies in our labs. No accelerator facility will get to such energies, can even hope to get to such energies. And this is, kind of, tens of orders of magnitude higher than what we can measure in our, say, the Large Hadron Collider, right? But the hope is that this physics actually gives rise to these fluctuations, and we'll be understanding a lot about the early physics in the universe at very high energies from this. So let me tell you what is there in the microwave background fluctuations. So what is there in the microwave background fluctuation, as I told you, is very simple physics, and that is why it makes it such a robust and kind of very reliable measure of what we understand of the universe. That's because the physics is very simple. It is the physics of a plasma. Plasma, you can imagine like the plasma screen to be a lake, surface of a lake, and that is disturbed, and there are ripples there, so there are sound waves, right? And that is what we are seeing when we are seeing the microwave background sky. So we are seeing a drop somewhere, or imagine a lake, placid lake, and there's a burst of shower. Around every drop there'll be a ring which will go out, and if I take a snapshot after 10 seconds, although the lake water will look choppy, we know that it's made up of this drop which created a splash here and a ripple which went out at a particular speed. In the same way, in the early universe, there were fluctuations. So the fluctuations were there everywhere at the same time, and they gave rise, each bit gave rise to a ripple. And these ripples combined to give you something that we see as the fluctuations in the microwave background. But we know underlying physics that there is a particular distance that this ripple could have traveled till the time that the microwave background screen was created, which is 500,000 years old. So it's speed of sound into 500,000 years, which gives you this. Okay, and then if we so when you have such phenomena, you have to look at it in what is called the Fourier space, or in terms of decomposition into what scales are the power in. And if you do such a thing for the micro background, it immediately sort of tells you, it gives you something called a power spectrum, which is like a curve of this kind. Any of these curves that you see here is a predicted curve for the fluctuations in this micro background for different values of various parameters like expansion rate, the total density of the universe, and total amount of ordinary matter. And it changes a lot as I change this variable. So it stands to reason that the day we measure this well, we will be able to say a lot about the universe. So for example, we know that the ripple went out, and it went out only with the ordinary matter being carried with the light, and hence the height of the first peak tells us the amount of ordinary matter that is there in the universe. And if it is consistent with our understanding of the early universe, we would think it should be at about 70 microkelvin. Similarly, as I told you, I'm looking at a plasma screen 43 billion light years away. And the plasma screen actually is decomposed into rings, and the rings of particular size. Depending on what is the curvature of the universe, the that angles in a curved universe do not add up to 180 degrees, right? So we know that this is a particular size, and we know the distance to this. This is the last category, this is the plasma screen. This is the distance, which is 43 billion light years, and this is 150 million parsecs, right? And then I can predict if the universe is like a piece of paper, then what angle should be subtended by this scale here? And that corresponds to the location of this first peak. And if it is a flat universe, then that peak should have been at 220. Okay. So over decades, in the 1990s, we had very coarse mapping of the microwave background. You can see that, the resolution is poor. It got very good in the next decade with another satellite called the WMAP, the Wilkinson Microwave Anisotropy Probe. And then it improved to what would be the ultimate kind of limit on what you can measure in terms of temperature fluctuations with a satellite called Planck, which operated from 2009 to 2011, but it took up to 2018 for the final results to come out. And then there are future experiments which are planned. All through this time, when there were the satellite experiments, there have been a lot of efforts from ground-based experiments too. And I won't go into that. But Planck produced really the most detailed picture of this plasma screen. So here you're seeing the plasma screen. The 3 Kelvin bath has been taken out. And then you see the fluctuations around it from minus 300 to 300 microkelvins in red and blue. So these are hot and cold areas of the microwave background over the full sky. This is the entire sky mapped into an oval. And this is a very detailed map of this plasma screen. What is the information encoded in this plasma screen? And this is the map which in some sense can be decomposed into dots with rings around them. So random dots with rings of a particular size around them, right? And we discussed that. So if I am really decomposing it into that, then I can actually tell you the geometry of the universe very well, because when I'm decomposing it, it looks like this power spectrum. And you can see the Planck measured the power spectrum very, very accurately, all on all scales, stretching from the entire sky 180 degrees to about a tenth of or 1/6 of a degree, right? So that kind of accuracy. And you can see that the measurements are very accurate because you can hardly see the error bars here, though you have to subtract the red curve out of those data points to see that there are actually error bars. Okay, this is how accurate it is. And what I wanted to point out is indeed the peak turned out to be 74 microkelvin, and the location of the first peak turned out to be 220, which told us that the universe was spatially flat, and which meant that one of the actors in our cosmological game is out of the picture. There is no curvature, spatial curvature in the universe. And then the game is between the amount of clustering matter and the amount of non-clustering matter, which we can figure out from the distribution of galaxies. And you can see here's starting from these tiny perturbations in the microwave background. If we run our simulations and ask what kind of a distribution of galaxy you'll get, without clustering, non-clustering matter, with or without vacuum energy, see that there's a marked difference, which we can measurably find out from our galaxy surveys. And we know that this is the universe which we live in. The voids are much bigger in this than in this universe. So we know that we are in a universe of a particular kind, which we also can reconfirm using these remarkable measurements of the microwave background power spectrum. Remember that Planck data points that I showed you here, they are shown in these green points here. And I can actually say that I don't know what the universe is. Let me just select 6 parameters, and I will keep varying the parameters. For every parameter, I can predict what the cosmic microwave background angular power spectrum should look like. And I can keep varying the parameters and ask what combination of parameters allows us to match this data. And this is what we actually do. And this is something that one of my students developed amongst many things. And you can see how nowadays you can, kind of simultaneously vary all the parameters, like dialing some knobs together, so that finally I get to a combination where the black curve actually sits right on top of the data. And I can read off these values, and these are our cosmological parameters. And remember, the CVMB physics is very simple and very well understood. So we believe these parameters. We believe that we know the baryon, which is the amount of ordinary matter density to 1%. We know how much of the matter is clustering, but not ordinary matter, but what is called dark matter, cold dark matter, uh, up to an accuracy of 2%. Okay, and so on. We know the expansion rate of the universe to about 1.5%. And so it's an amazing time where the microwave background has allowed us to understand how the universe evolved from when it was 500,000 years old to now. Okay, that's a considerable amount of the part of the history of the universe that we already have understood. Okay, and that is consistent with a very one of the simpler models of cosmology. It's geometrically with spatially flat. Spatial geometry is flat. It is dominated by, it's called lambda domination, is domination by something called the cosmological constant, or equivalently something like a vacuum energy, and cold dark matter. And you essentially need 6 parameters to explain all that we see in the universe at this time. Okay, so it's amazing. The story looks very simple because we have a simple model. There are only 6 numbers that we are playing with. Yet, uh, we know that the universe we have discovered is very exotic, because 95% of the universe is in some exotic form, because the matter that we are made up of and we have seen our labs, and that the world of atoms and normal matters of electrons and quarks, that only constitutes 5% of the universe. Rest of it is made up of cold dark matter to some extent, which is about 35%, and then the rest of it is some mysterious non-clustering matter, which we call dark energy. Anything we don't understand in cosmology, we attach a dark label to it. So dark matter, dark energy, and dark energy is non-clustering. But the best explanation for that is a non-zero cosmological constant. The general relativity that allows you to have a fundamental constant called the cosmological constant. And if that is non-zero, then that also would explain this energy density. Okay. But what is the next step? Remember, I hinted on that when I was talking about this plasma screen. I said there's this plasma screen from where whose perturbations we are measuring in the microwave background, which tells us how galaxies formed into this rich structure of distribution. And then we inferred all about cosmology from there. But remember, the question that remains is what perturbed that screen at all. So remember that what we have dealt with is starting from a universe which is about 500,000 years old, with some tiny perturbations, we understand how the universe can evolve to what it is now. And that the standard model of cosmology that we have now explains very well. But it still remains to be answered what gave rise to these fluctuations that we see on this cosmic IMAX theater in the first place. And that answer is hidden in our understanding of the early universe at very high energies. Energies, as I said, far, far, far beyond the axis of any conceivable accelerator physics. Okay, and we believe that during that time, there was a phase when the universe expanded extremely fast. It's an accelerated expansion. So, for a time, it was expanding exponentially for a short time, but it expanded by huge factors in that short time. Right, factor of 10 to the 28 in a matter of 10 to the minus 35 seconds, say. Okay, and that violent expansion that we had actually stretched quantum fluctuations to become classical and lead to these fluctuations that we see on the cosmic screen. So it's an amazing story. Now, one would have thought, oh my God, this is again a fairy tale. But remember, we had told you a fairy tale earlier of small perturbations in the plasma screen, which would grow by themselves by gravitational instability into giving you this distribution in galaxies that we see now. That was almost like a fairy tale itself. There's a plasma screen and it's oscillating like a elastic membrane, and the sound waves on it, which we are seeing as distribution of galaxy. We have verified that very well. So now we are more ambitious. We want to see if our guess about the early universe is correct. And to do that, we need to now go back and call our old friend the gravitational waves. Because remember that this cosmic screen also screens out any information that you can get from the early universe in electromagnetism. Almost all information that you can get there. Okay, nothing directly can come across this cosmic screen. However, gravitational waves can come right from the origin of the universe, or from this inflationary phase. And if our understanding of how inflation could give rise to these fluctuations in the microwave background, which has grown to become the galaxy distribution galaxy, and even the galaxies themselves, then the same physics tells you there would be a background of gravitational wave that you must exist in the universe. Only thing uncertain is how much of gravitational waves we have relative to how much of perturbations we have which relate to the galaxies. Okay, and that is encoded in an unknown number called R. And we are already starting to put limits on it. So at this point, R stands at about 3%, right? 3 parts in 100. Okay, but we need to really dig further down. And it's a to-do and must-do for cosmology, because that will nail for us our understanding of what happened in the early universe, which gave rise to the perturbations, which we have used to understand all the cosmology. It's a must-do for cosmology. And of course, the entire world, there are the community of cosmologists, there's a significant community of cosmologists working on that. So again, go back to the plasma screen. See, at this point, I've been talking only about the temperature fluctuations here, but there is also a net polarization fluctuation. Okay, and what happens is, if there are gravitational waves from the beginning of the universe, the gravitational waves are on almost large wavelengths comparable to the size of this plasma screen. Remember, the plasma screen is 43 billion light years in radius, so 86 billion light years across in diameter. So they are waves, gravitational waves of that kind of wavelength. Okay, and what they do is they create, allow this plasma screen to become a gravitational wave detector. Just like if you have heard talks on LIGO, you know that on 4 kilometers there are mirrors that move minuscule amounts because of gravitational waves going. What happens here is, because of the existence of gravitational waves from the early universe, this plasma screen distorts to something like this. Okay, and of course it's not as exaggerated as this, is hugely exaggerated, but the distortions are at the level of 10 parts per 100 parts per billion, for example. Okay, or even stretching to 1000 parts per billion. And then I would find some way of seeing whether the plasma screen has been distorted by gravitational waves from the early universe. So if you go back to this map of the sky, I have shown you a very high resolution temperature map. This is a low resolution temperature map to highlight the fact that there is also information in the linear polarization pattern. So if I look at light, you know that light has intensity and it can be also polarized. and cosmic microwave background happens to have linear polarization. And in any direction, there's a particular stick that I can draw, which tells me the polarization of the light coming from that direction. And this creates a pattern on the sky. And to detect gravitation, and this pattern is at the level of a tenth of the amplitude of these temperature fluctuations. The temperature fluctuations are at 70 microkelvins. The polarization is a tenth of that. But we are looking for a signal that is again a factor of 10 to 100 times that, right? Times smaller than that. And these are particular patterns of the stick. The patterns of the stick have holes in them. They are not radial or tangential, but then they have this cartwheel kind of a structure. You can see that it's as if things are being twisted around like this in a vortex. And these whole patterns of vortexes in the pattern are what we are looking for, because they will be telltale signature of primordial gravitational waves originating in the universe. To do that, we'll have to dig very deep in sensitivity. So at this point, this is the power spectrum that I showed you earlier. This is the power spectrum of one kind of polarization pattern, which is related to density perturbations, which is already measured. So at this point, our sensitivity in terms of power that we can measure at different angular scales is up to this. So we have information in this cyan band. But to know about gravitational waves from inflation, I would need to dig further deep down, and I have to have experiments which have better sensitivity and cover this yellow region. And to do that, amongst many other proposals around the world, we have a proposal to the Indian Space Research Organization called, from a consortium called CMB Bharat. And the satellite mission is called ECO. It's exploring cosmic history and origin. And this is a multifaceted science and astronomy mission that will map all the information that is there in the microwave background sky at many, many frequencies. I won't get into why, or maybe I can answer in questions. And it will get this pattern that we are looking for. So because it will have unprecedented sensitivity, accuracy, and angular resolution. And its scientific promise is a very good chance at detecting primordial gravitational waves, which will reveal the signature of quantum gravity. But then in doing so, it will also, give you a lot of information about neutrinos, the dark matter in the universe, and many, many other things as byproducts. But the main prized goal is the search for gravitational waves from the beginning of the universe. In order to increase the sensitivity, we need to, kind of forge forward beyond frontiers of how small a power that we can measure. In our daily experience, we talk about a megawatt power plant and say milliwatt lasers. And you may not know this, but already your cell phone is an extremely fine detector of power. It can detect power at picowatts. Okay, in fact, even tenth of a picowatt. But to have detectors that can measure power at the level of attowatts. Now, this cell phone receivers detectors are things that were actually in the lab and led to many of the things in the early days of CMB many years back, right? In the early late 90s, what is coming out as 5G used to be in the lab there. So now in the lab we have things which can get to this attowatt sensitivity. We have to have that, but extremely delicate, because they are measuring picowatts of things. So you have to put them in an environment which is extremely cold. So you have to hold this detector in this is basically a schematic of the satellite. And you can see that there's a thing which takes the microwave background and focuses it on this. There's of course a lot of optics here, which is simplified, and this is the focal plane. This focal plane has to be at 100 microkelvin. Okay, but remember the spacecraft is actually has solar panels here and is actually measuring is at a temperature of 300 Kelvin, like room temperature on this side. So you have to have very amazing amount of thermal design to make sure you isolate this hot part of the spacecraft from this cold part, and that is done through very intricate cryogenic cooling chain, space qualified cooling chains, which are themselves very high technology, which we need to bring in to launch such a satellite, which will keep the hot part, which is at room temperature, from something which is maintained at 100 millikelvins. And what is there is an array of small detectors which give you this attowatt sensitivity. Okay, and you can pack together, here in this design we have 2400 detectors. In this we have 7800 detectors, so it depends on what we can manage, but these detectors are real. Such detectors exist, and they are being put on ground based telescopes as we speak, right? And these are called transition edge sensors, superconducting. These are at basically at the at millikelvins, because of the fact that you have to look at superconducting, a transition from superconducting to non-superconducting phase of a transistor. And then you pack that whole thing into a spacecraft, and you can already see the optics is more complicated than what I told you. There's the overall shield which shields it from here, and this is the side which will face the sun always, and it will be launched away from Earth to something called the second Lagrange point. So this is the Earth Moon. We will go very far away, and there is a quasi-stable point where we can park ourselves and monitor the sky from there. And to get that far with a payload which is about 2 tons, we need to use the best launch capability that we have at ISRO, which is our GSLV Mark III. The GSLV Mark III, if you remember, was the one which took you to Mars. And this is, we will have to launch it towards Sun-Earth orbit in L2. So I will conclude there. So you can see there's a very amazing story of cosmology that has unfolded in the last few decades, and culminating in these amazing results from Planck. In fact, the last year's Nobel Prize to Jim Peebles in 2019 was actually not last year's, last year's now, was to kind of celebrate this huge advances made in understanding a standard model of cosmology. But we have to understand our origin. We have to understand the origin of the universe. And maybe the next generation Cosmological Background mission that will be launched could be from India. And with that hope, let me stop and take questions. Thank you.
Thank you, Tarun, for taking us through that physics journey on a stretching membrane, and also the telling the viewers about the exciting eco possibilities in the offing. And there have been a number of questions. Actually, if you would come to this window,
Okay, I
uh,
will stop sharing
no,
then.
you would be able, yeah, yeah, you would be able to
Okay,
see as I flash the questions, and I see that some of them actually you answered as you went along, but maybe we'll still take the questions even at
sure.
that. Hmm? So, all right. And so I'm starting actually at the bottom end, the last question first. And I think this must be referring to the gravitational waves, right? All
So
right.
this Vishwajit
So,
Jana?
so I think where gravitational wave lies in this spectrum, I think that is what he means.
No, Vishwajit Jana asks, how do we define cosmic radiation? In what part of the spectrum does cosmic waves lie? So they are in the millimeter wave. So it is higher frequencies than radio, but lower frequencies than infrared. So this is what is called the sub-millimeter band. So that's where millimeter and sub-millimeter band is where the micro background lies. So if you want to know in numbers, it's between say some uh, 60 gigahertz to about 1,000 gigahertz. But the most sensitive area is 150 gigahertz.
Then Biswajit Jana again. Uh, Gravitational waves, energy associated with it, and also in
Yes,
terms of
so
the
they
need for
exactly. So
quantization.
gravitational waves have energy associated with them. In fact, that initially for many decades was a puzzle. You know, people were not sure if gravitational waves were real, but in the late 50s, people got together and concluded that gravitational waves do carry energy and momentum, and they are just like light carries energy and momentum. Gravitational waves do that, and just like light in the quantum theory is made up of photons, we do expect in some quantum version gravitational waves are also composed of gravitons. But that quantization of gravitation, as you may know, is still an incomplete search.
Yeah, I was actually thinking at that time in terms of the multi-messenger kind of possibilities which are there, and whether that was what was implied there. All right, so that's Biswajit Jana's question one and two. I see. Ah, yeah. Okay, Priyabrata. That I'm trying to flash this. I have a little bit of problem. Sometimes maybe I'm flashing the wrong one, but right now it has come the correct one. What will happen to CMB after billions of years? Priyabrata.
Same, yeah, billions of years later, the CMB will get even colder. Okay, so in billions of years, the universe will have expanded more. The CMB will have become colder. But also, if you're asking about the spectrum of microwave background fluctuations, they will also evolve, but on the scales of billions of years. If you want to see that, you should visit the web page of Lyman Page. One of his undergraduate students' projects actually worked out the CMB power spectrum that will be, fluctuation power spectrum that we measured by an observer, many, many billion years later.
Could you spell the name?
Lyman Page,
Okay, okay.
the Princeton faculty.
Uh, and this, I think, I mean, you did answer this, but perhaps let some more comments.
Yeah, so there is no massive structure that exists in the early universe. So it's not as if there are black holes merging. So this origin, as I said, is very different from the origin of gravitational waves that we are measuring with LIGO, or we will measure with LISA or pulsar timing. There are compact objects which are falling into each other. There's motion of matter. Here, there is actually shearing of space-time, which is creating these gravitational waves. But the shearing is coming because of quantum reasons. This is basically because there is a degree of freedom of in which space-time can be shared. The quantum fluctuations will take that and create these gravitational waves. So it doesn't require massive compact objects. But the energy comes from the fact that you're talking about extremely energetic universe. The radiation, or at that time was 10 to the power 16 giga electron volt, right? Energy scales. So there, any sharing that happens generates very large fluctuations.
Vivek Pathak uh, is asking why
Yes, so
vacuum.
vacuum energy can't explain the expansion of the universe by orders. So that's precisely why I kept talking. In cosmology community, we talk about a cosmological constant because that's a constant, fundamental constant, and so just like we may not ask so much as to why the gravitational Newton's constant is whatever it is. Similarly, the cosmological constants happen to be small. Yes, if I want to interpret it as vacuum energy, then it's a problem because there has to be, we know that vacuum energy is real, and quantum fields do have vacuum energy, but we believe that they can be understood to be kind of zero, but that is a problem when you have gravitation involved, because when we set that to zero in the absence of gravity, that is fine, but in the presence of gravity it poses a problem. But if you want to look at vacuum energy as kind of the 0 point energy, it is given by the scale of the physics you're looking at. And even if we think of scales of TeV, then we miss the energy density by a huge amount, by these 130 orders of magnitude. So vacuum energy is not really easy to explain, use to explain the cosmological constant that we measure.
Vivek Pathak asked something, and then I think Vishwajit Jana was partially referring to that and has his own question. So maybe I will flash both. This is Vivek
Okay.
Pathak.
Yeah, so
And
can we distinguish whether a galaxy lies on this ripple? Yes, so baryon acoustic oscillations, we do measure, uh, this ripple in the distribution of galaxies. Now, it's not as if there's a cluster lying on the ripple, but basically what happens is this is there everywhere, right? So I told you there are raindrops falling everywhere, and there's a ripple around it. But now, if you choose one of the places where there's a maximum density, then around that, the density will keep falling off. And then at about 150 megaparsec, you see a little excess of galaxies. And so that is true. In that sense, relative to a location of a cluster, you will see that.
so Vishwajit Jana, he was responding through that a little, and then he has this question.
Yeah, when we detect a gravitational waves, we detect only. Here we are not even seeing the wave in action, because wavelength is on cosmological scales. Some I told you, like wavelengths of 43 billion light years. And now, if we imagine their time period, then we will have to wait billions of years for the wave to. So we see a static image of the gravitational waves. So it's not as if there's a wave passing by. It's the time period is so large that it's like frozen for us.
Okay, now I think there are also some questions from uh, there are school as well as college students in the group who are there. Uh, this probably is a common question which does arise to someone encountering these topics for the
Yeah.
first time.
So there is no center to the expansion of the universe. The universe is expanding everywhere. Okay, so it's not actually. I somehow sometimes find that when we have these BBC serials, they kind of show you a hot ball expanding out. That's not what is happening. The universe is actually expanding everywhere, around every point. So there's no center to the expansion of the universe.
Yes. Kiran Mehta had this question. Uh, yeah. Size of the universe.
Yeah, so this is size of the universe in the sense you're saying the distance to the plasma screen is 43 billion light years. Why is it not 14 billion light years? Because that is the speed of light into 14 billion years. That's because of the expanding universe. You remember that light travels more in the early times because distances are smaller, and but later the universe is expanded. So what light covered in this first bit actually accounts for a lot. And if you take an expanding universe, you can show that there is this factor depending on the expansion history of the universe in our standard universe. there's a factor of about 1.7 which comes in here.
Kiran Mehta also had this question, and I was texting him that saying that perhaps these asymmetries, etc., it's a much larger scale that
Yeah, so why
homogeneity.
do we reason homogeneity mathematically? Although we have, yes, but the we also know that inhomogeneity dies out as you look at average on bigger and bigger scales. Although we see clusters and superclusters of galaxy, I told you, those are on, on the neighborhood scale. But if you are kind of averaging the universe on sizes of 200 million light years or few hundred million light years, then you will find that the universe, even the distribution of galaxies on the average, very smooth. But the strongest reason for homogeneity comes from the fact that the cosmic radiation, uh, the dominant radiation form in the universe, which is in the cosmological background, itself is extremely homogeneous.
Okay, since I was putting his questions, let me just put one more too. The inflation of mass of the entire universe caused the gravitational waves. That's also from Kiran Mehta.
No, no, actually, it's not easy to imagine this in terms of masses, and it's more to do with kind of quantization of degrees of freedom in space time. So I wouldn't want to imagine that you're thinking of something sloshing around.
Related to that, Sahir Ahuja also was asking this. He has two questions which I think get related. He just wants to, after this, he also wanted to you to explain the cosmic gravitational wave detector.
Yeah,
What,
so cosmic
what is it and
background
what?
from inflation, as I said, is of quantum origin. And we believe this physics that gave rise to fluctuations, that gave rise to density perturbations, which gave rise to the distribution of galaxies we see, uh, also creates gravitational waves. Okay, and this actually is again a random noise kind of background, and hence it's called gravitative background, and it originates from inflation. It doesn't cannot be thought of decomposed in terms of masses oscillating and things like that. It's not easy to think of it like that. It's not probably also correct to think of it like that. Now, what is the cosmic gravitational wave detector? It's like I told you, there is actually we see that there is a plasma screen surrounding us at 43 billion light years. So it's like imagine you are sitting in an IMAX theater and there's an earthquake. The theater is going to oscillate, right? And some part of this, so you will see that distortion to the images there. Similarly, if the universe had gravitational waves from its beginning, then they kind of rock the uh, plasma detector, right? Rock in the sense you don't see it shaking, but you see it distorted, because the distortion is going to change only on the scales of billions of years.
Astro Explorer wants you to give
So
information
how's the
about the
experimental
setup.
science? Okay, so the LIGO India has two aspects to it. One is the construction of the facility, which is going well, and there is also a training and R&D program, which is spread across about a dozen institutes in the country, where there are researchers working on cutting edge aspects of gravitational wave experiments.
Yes, I thought you would need no a whole talk for this because many of the questions might be like that. And yeah, she is asking Priyabrata whether this I think you touched upon a little.
Yes, we need to. We at this point predict these gravitational waves based on an approximation to quantum gravity called quantum field theory in curved space-time. And if this is borne out, then we know at least our approach to the theory of quantum gravity is correct. Okay, we don't have a radical problem there.
Okay. In some cases, actually, the participants have been answering each other's questions, but I mean, I thought maybe you might still want to comment on it. Uh, this is whether this was answered correctly. You want to comment on it?
That's correct. Yeah, the micro background itself is universe is
So no, yeah, yes. So we do have very en- enthusiastic participants who keep answering each other's questions.
that's very nice.
That was very
Makes
nice.
that much easier.
Okay, I think if there are any other questions, you please post, or if I miss something from above, please post it again. Okay, Astro Explorer has this question. Massive objects cause dip in space-time fabric. Then why we are seeing stars and northern sky? All stars are heavier.
No, no. So it's not as if
I
the
think
dip is, So you have to imagine the dip is in a space that is three-dimensional. You're imagining the Earth floating on some surface, which is and dipping it. That's not what is happening.
yes. So I think I have picked up. There were earlier there were a couple of comments like thing they are not questions, so I am not picking those up. But if I missed any question above, please type it again before we will be ending the broadcast. If any question has been missed, and Tarun, thank you for answering so patient.
No,
We have a
no,
mix of participants, no school as well as
no.
college,
That's
so
good. That's
we
nice.
have
I
wide
just
spectrum of questions also.
Yeah, I know it's a fairly technical area, but I just wanted to convey the excitement of what's happening in cosmology, and particularly for young people, they would be the, people attacking age when these will happen.
You were saying that if there are questions, you would tell us a little more about the different frequencies for detection in echo.
Oh, yeah, that is because we have to peer at the microwave background through the emissions in our own galaxy. And that we kind of clean out because that galactic emission depends differently on frequency than the microwave background. And we can clean it out by using measurements of the microwave sky at different frequencies. So we have many, many frequencies, and that allows us to clean this better.
Uh, I think there was one more, sir. Just if you don't mind. Okay. This was more of a general thing that Mr. Jana wants to know what would be the possible opportunities for undergraduate BTech students. Also, there is this the LIGO educator or program, something
Yes,
of
so
that
there's the
like.
LICO underscore outreach, and
Mm-hmm.
you can reach out there. There is, in fact, also a website link where you can post your CVs, and we look for project students there with engineering background. So, first of all, let me tell you, I am myself an engineer, so you can change into physics and work in with but even as an engineer, you have also a lot of roles. So you can see in LIGO India itself, there are various aspects of engineering that is important and will keep becoming, will stay important all through. Even after we have built the detector, as we improve it, we'll need more of mechanicals, control systems, electronics, all branches. Similar case with CMB Bharat, the eco thing. It is actually very high-end uh, electronics and thermal modeling, as well as there is a lot of control theory there too.
Viswajit Jana was asking for your contact, etc. But I just wanted to ask you this: that
Hmm.
would it be possible, because many of the students here do have some they have been trying to do a little bit of quantitative follow up after the talks.
Hmm.
Is there any project which they could take up uh, with maybe some coding skills in
There
Python?
are projects, but we are getting a lot of requests. So what we have is a portal. I will see if I can quickly post that on the chat.
Hmm.
Will that show up there? No, right?
Yeah, if you post it in the chat, it will show up. I don't know whether it stops links, but let's try that if we can put that out. Else, also, I think Biswajit, you are there in Astro Adda group, right? So we can post it there, and um,
Yeah.
sometime I mean
So I
I've been
will
asked speakers if they would join this WhatsApp group for
see
students to ask
this. This is
later.
what I typically send out. So there is a gravity wave research opportunities,
Yes, that has come
link.
to me in private chat. Let me try to put it out in general chat. And so before we end the broadcast, so that this would go, yeah, it has gone into the chat. So yeah, the opportunities which you are suggesting are possible for undergraduate students.
This is so we actually have a kind of a window where we collect these and then then try to put them into various projects that we have.
Hmm.
But I must tell you that we get lots of requests, and at this point, our community is not big enough to support as many people. But we will slowly become bigger and bigger, and we'll do that.
Biswajit, Tarun's contact would be on the website of IISER and also perhaps on
Yeah, yeah,
IUC.
sure. I
Yeah,
mean,
yeah.
people are welcome to
I
write
got
to
it.
me.
Yeah.
Yeah,
Yes, yes.
please email me, and I can.
Huh. So, thanks so much, Tarun, for
Okay, no, thank you. It's a
through
pleasure.
this complex field for giving a kind of a user-friendly feel to all the. There are few
Okay,
more,
thank you.
one or two I think have come in. Is it okay? Is this
Yeah,
should
sure,
I
sure.
flash that? Uh, is there any prospect of seeing? Uh,
Yeah, gravitational lensing is seen in the microwave background. It's actually one of the things measured by Planck. And in fact, one of my former students, you may have seen him in Ayuka, Shubhadeep, is even also working on the effect of gravitational waves to be seen in the microwave background. And there are exciting things that are possible, yes. But yes, gravitational waves themselves lens, and cosmic microwave background also is gravitationally lensed.
Okay. So there is a general question by a student who seems to be interested in research, but the parents would not facilitating it. These issues do come up for many young people. These issues are there, and perhaps parents think about what may be the later on career issues and so on. The thing is that what you are interested in some case, I mean, try to pursue it in whatever way, whatever opportunities which now if there are many people who are not getting opportunities, maybe because they have not crossed the undergraduate postgraduate appropriately, but they're still interested in research. So look for possibilities with which you are able to just stay true to your interest, while at the same time, I guess, I mean, you would have to follow your uh, parents' advice and so on. Okay, so I think we will close this session here. There are no other questions which have come in. Thank you so
Okay.
much, Tarun,
Thank you
and
very
thanks to
much,
all of
Rana.
you.
Yeah.
So I'll end the broadcast here now. I don't see any questions. Suddenly.